Hello everybody, welcome to section 6.1. We're going to start chapter 6 looking at the different names of polygons and how we find the total angles in all these figures. So before we even fill in the blank in the top up here, we can fill in the first row. We know from previous work in previous chapters, a triangle is a three-sided figure creating just one single triangle in the picture, and we know that triangles add up to 180 degrees. The purpose of this section is to say what happens if we go beyond that. So what if we create a quadrilateral, pentagon, hexagon, hepta, octa, nona, deca, and beyond? The number of sides that our polygon has is directly responsible for determining the total degree measure it will have inside of it. So take a look at the quadrilateral here. We have a four-sided figure, but if we draw this diagonal, we end up splitting it into two triangles, and as a result, we get 360 degrees total for the angles on the inside. If we follow that same train of thought, a five-sided figure, but if we draw the diagonals in the pentagon, it creates three triangles, which in turn bumps us up to 540 degrees. And if you take a look at the hexagon, a six-sided figure, but drawing the diagonals in, creates four separate triangles, which now brings us up to 720 degrees. For the 7, 8, 9, and 10 case, let's expand on this, but we don't want to do it with the picture because we are trying to develop the actual formula for finding interior angles. So the key is to start looking for the pattern we're generating. Three sides created one triangle, four created two, five created three, six created four. Keep that same pattern going. We must end up getting five triangles built out of the diagonals of a heptagon, six built out of the diagonals from octagon, seven built out of the diagonals from nonagon, and eight built out of the diagonals from decagon, which means we'll add another 180 degrees for each of these rows. That'll bump us up to a total of 900 degrees for the heptagon, 1,080 degrees for the octagon, 1,260 degrees for the nonagon, and 1,440 degrees for the decagon. We have generated a pattern here. All we have to do is build a formula for it. We are looking at the number of sides that our figure has is always creating two less number of triangles, and then every triangle was worth 180 degrees. So let's formally put that formula together. The total degree measure for the interior angles in any polygon is given by the formula n minus 2 times 180 degrees. So the number of sides that we have, minus 2, times 180. Now, as an extension of this, if we get told that we have a regular polygon, all the sides and all the angles are congruent, we can find each individual single angle because we know we can divide it by n and figure out what each one measures. They all have to be the same. So that formula at that point just simply becomes n minus 2 times 180, but we take that result and divide it by n. So if you get the regular case and you want to find a single one, we're just simply looking at dividing by n to compensate for that. Now, if you want to do exterior angles, we have two ways we could look at this. If you know the interior angle, so say you were doing this work earlier and you had to find the interior angle, you could simply do 180 degrees minus the measure of the interior angle, because we still have the same rule from all the way back in the very first chapter. An interior and an exterior angle are side by side forming a straight line. They have to add up to 180. So if I take 180 minus the interior, I have to know what the exterior one is. Now what happens in a lot of problems is what you run into is you don't know the interior part at all. You only know the exterior values. So the other possibility is 360 degrees divided by n. It is a guarantee that the exterior angles will always add up to 360 for every single polygon, no matter how many sides it has. This formula is why interior is highlighted and bolded here. This formula is only for the interior angles. Exterior is a fixed value at 360 and then divided by n because it was regular. As far as problems go, we're basically looking at know the names of your shapes and perform the computation correctly. So for example 1 here, we're asked to find the measurement of a single interior and single exterior angle for a regular, so that gives me a giant hint, and then pentagon, penta meaning I must have 5 sides. Now, simply build the formula and calculate away. 5 sides minus 2 times 180 degrees comes out to be that the entire pentagon as a whole must add up to 540 degrees. Now I can apply regular. If I take 540 degrees and divide it across 5 angles equally, every single one of them must come out to be 108 degrees. So there's my single interior angle. I can just as easily take 180 minus the 108 I just found, and I would know that every exterior angle is 72 degrees. As an alternative, which I'll just put a note here, alternately, we could just simply take 360, the total of the exterior angles, and divide that by 5. That would give me 72 just as easily as the other version did. Either one of these is an acceptable step. There is no rule that says which way you must solve it. Honestly, it depends on the problem. Look at whatever information you're given and use whichever method works best for your question. You'll see that coming up in one of the last examples down at the bottom of the page here. All right, for example 2, we're asked to find the total of the interior angles for a 15-gon. Well, we haven't discussed this at all, so let's have a quick little side note here. 15-gon is literally telling me that it's 15-sided. When we get beyond the names that were on the first page of the notes, so past decagon, anything past 10-sided, we generally just name it n-gon, with n being whatever number it is. In this particular example, 15 sides. As far as the problem goes, that doesn't affect us at all. It's just simply plug and go. So 15 minus 2 times 180 degrees. We'll go calculate that out. 13 times 180 comes out to be 2,340 degrees, and that's exactly what I was asked for. I was asked for the total measure of all 15 angles. They add up to 2,340 degrees. That's all I have. All right, for example 3 here, we're asked for a single interior and single exterior angle to a regular 24-gon. So let's use the same approach we did in example 1. We know we have 24 sides, thanks to the name 24-gon, so let's go calculate it. 24 minus 2 times 180 degrees will come out to be a grand total of 3,960 degrees. Now, let's use that number. I'm going to take that 3,960 degrees and divide it equally across 24 angles, because that's what regular tells me to do. So if we divide that by 24, we get that each angle is 165 degrees. Also, if we take 180 minus 165, we know that each exterior angle is 15. Or we could have just simply done 360 divided by 24. That would come out to 15 as well. All right, almost last one here. We have one last thing to discuss after we finish this last example on the page. If each exterior angle for a regular polygon is 40 degrees, we're asked to name the figure. So we need to figure out how many sides it has. So this is a case where we want to specifically use 360 divided by n, and that's going to come out to be 40 degrees according to the setup of the problem. Every exterior angle, so the 360 total divided by how many there were, had to end up being a 40-degree angle. Let's go work out the algebra. If we multiply both sides times n, 360 is equal to 40n. Divide out the 40 on both sides. We end up getting that n is 9. We were asked for the name of the figure, so 9 sides means we will call this a nonagon. The only other thing to tack on to the last item here in the notes is every once in a while you get your problem drawn as a picture instead of all of these algebra type problems that you've seen here. You solve the picture ones in the same exact manner, you just have to count the sides yourself. Like for example, if there was some figure drawn, which let's draw this, and then some algebra was written in each of the angles, and it asks you solve for the value of x in this picture, you would have to count it yourself. There's 1, 2, 3, 4, 5 sides, so we'll call it a pentagon. Courtesy of the work we did in example 1, we know these 5 angles all add up to 540 degrees. You would take each algebra expression, add all the like terms together, and set it equal to 540 degrees. The picture problems are solved in the same exact manner as the algebra ones. You just have to build the algebra yourself out of the picture. That's everything for section 6.1. If any questions pop up, make sure to give any of your teachers a quick question and find out what you need help on. And see you everybody in the next lesson.